All right, so let's continue the review here. We're on section 3.10. This section deals with solutions. Now, all along, we actually have been dealing with solutions, and one of the main things that we've been talking about in this section is for solutions, we know that we've got a solute. That's the item that's going to be dissolved, and that solute is being placed inside a solvent. And so together, these items then essentially is going to be known as that solution. The solution is going to have a concentration. That concentration is essentially the number of moles of the solute divided by the volume of the solution that you're in liters. That's a very specific unit to have here. So that's moles of solute in the numerator. And so knowing how to prepare this is going to be important. But this section then requires that you know a couple of items. So one of the first things in this section that you need to be able to do is to identify whether something is going to dissolve or not. So there's a lot of rules for solubility. And so solubility here, and so let me spell that right, solubility. These are some rules that you actually need to make sure that you can commit. You had an opportunity to do this already. So one thing that I will show you here on the screen is going to be that solubility table. At the very least, you want to know about this. So let me bring that up here for us in a second. So here is the solubility table. Let's go to make this a little bit bigger here. And so when you look at the solubility table, it should help you identify what some of those rules for solubility, at least I would spend a little bit of time focusing in on the more predominant forms of solubility or insolubility. So here on the table, you've got a couple of items here. Everything that shows up in SOL or in white color is something that essentially is identified as a soluble. Now, the gray areas here represent things that are soluble slightly. And then the areas here in red, as we recall from class, these are the ones that are not soluble at all. So if you want to kind of relate these to the attractive forces between solvent, and solute-solvent, the ones that have the weakest solute-solvent forces are the ones in red, and intermediates having a moderate level of interaction between solute and solvent are the gray ones, slightly soluble, and then the ones that have the highest level of solute-solvent interaction are the ones that are white here in terms of soluble. Now there's a couple of general trends that you can identify here. Remember here we had a list of solubility rules that I have shared in the class. However, if we use this particular solubility table here, we see that group 1 metals is identified here, and for the most part, almost all of the group 1 metals are going to be soluble. There is one exception here, and that's going to be when phosphate combines with lithium. That would be insoluble. Most of the group 2 metals are going to be soluble. There are some notable exceptions, and so clearly here phosphate's going to be insoluble, carbonate's going to be insoluble. Hydroxide is mostly going to have a mixed review here. You have solubility with barium, but magnesium is insoluble, calcium is slightly soluble. So what we see here is the size of the atom matters. Barium here is going to be soluble, and then over here, when you have the group 2 metals combining with fluorine, we see mostly insolubility here at the very top. Now, transition metals, you're going to get a mixed bag here overall. For the most part, you see that transition metals tend to have insolubility spread out throughout. However, there are exceptions. And so instead of looking at the actual cation side of things, you can look at the anion side of things. And notice here that nitrate, no matter where it is, in terms of first group 1, group 2, or transition, nitrate is always soluble. Same thing goes with acetate here at the bottom. The only exception there is going to be aluminum at the very top. You can see that when it combines with acetate, it's slightly soluble. But you can look at this table here and use it to actually get a good understanding of the solubility table. You can also, as always, go and look at the actual solubility chart, the summary of rules that I shared with you in class. Let's see if I can put these here on the screen for you. First, let's go ahead and move this out of the way. Let's go ahead and move this over here, and then I'll put this here at the bottom. Okay, so here's the summary of those rules here. And so you want to go ahead and take a look at this and just go through the pattern here. If you want to pair it up with the other solubility table over here on the far right, you can see that there is a lot of overlap in terms of the trends that were there. The beauty of having this one here is that you've got some examples here of some of the compounds. Notice Cabasser shows up various times throughout the whole thing. Notice calcium, barium, and strontium here. They typically are exceptions to some of the rules, so it's important to kind of notice when they're there and when they exist, as that could also help you identify solubility for a lot of these compounds. So aside from that, though, the other item that you needed to pay attention to in this particular section was some of the factors that affect solubility. So let me move some of these items over here to the side, and then we'll go from there. All right, so what we're going to do here is we're going to move solubility. Let's move this over here to the side that way, and that should give us enough of a space here to continue our discussion. So some of the factors that affect solubility are the ones that we had talked about in class, and so those factors here include one, the temperature. So let's just abbreviate that as temp. Number 2 was the polarity. 3 was pressure. 4 was the size of the molecule. And then lastly here, the 5th one was going to be the level of interaction. Okay. And so the main thing I need for you to do is kind of go through each one of these and understand the relationship versus solubility. So let's kind of do this here together. So when temperature goes up here, as temperature goes up, what we tend to see is that the solubility is going to go up. And so that's very important for us to consider as a trend. Now, this is going to be true here when we consider both solids and when we consider liquids. This is not going to be true when you consider gases. So for gases, this is not so. So the trend there when we see this is going to be for the gases, where we're going to see is a slightly different trend. So the trend we see there is as temperature goes up, the solubility here goes down for a gas. And so you got to just generally know that particular trend overall. The other item that we need to look at here is in the second category. When we talk about polarity, what we're really talking about is going to be the polarity of the individual molecule that's being dissolved. And so typically here, the trend for the polarity would be as polarity goes up here, then that actually leads to a higher increase in the intermolecular force attractions. And so this is going to be leading to an IMF increase, and that IMF increase is essentially going to lead to a higher level of solubility. And so that's an important here. Now, if you had reduction in polarity, obviously you might still be able to get some kind of attraction going on there on the nonpolar side, so we'll have to consider things like London dispersion forces. But overall, the level of attraction is going to drive the whole solubility. So the stronger the attraction there, whether it be on the polar or the nonpolar side, the greater the solubility that is going to exist. So the next item here was the pressure, and pressure is going to be very similar to what happened with temperature. There's a variation here that we notice. Among the solids and the gases here, what we see here as pressure goes up, it really has no effect on the solid and the liquid. Where we do see the effect, that's actually going to be for gases. So for gases only here, what we see here as pressure goes up, so let's put this here, as pressure goes up, what we tend to see here is that the solubility also goes up. But remember, that is only true of gases, and so you got to be very careful with making that assumption. Pressure does not affect solids or liquids. Now, the size of a molecule is important because essentially here, as the size increases, then that means that the surface area of that particular molecule relative to the mass is actually kind of low overall. So size is actually going to have the inverse relationship here for solubility. So as size goes up, solubility will go down. And so that's going to be true there of pretty much everything. And largely, again, like I said, what's going on here is it's a matter of surface area. It's a lot harder for something that's really big to get dissolved by the solute. There has to be a lot of interaction. So a way to alleviate that would be to look at the last section here, is looking at the level of interaction. If the level of interaction stays the same, then yeah, the size really is going to have a huge impact there. But if you're able to increase the level of interaction there by doing several things, one of the most common things you can do here is to agitate. And so let's kind of clarify here the level of interaction here. We're talking about agitation, shaking. This type of agitation is essentially going to lead to the following. So let's just say that if we do increase the agitation, that's actually going to lead to an increase in the solubility. Okay, and so those are the trends that we typically are aware of, or should be aware of overall. And so make sure you review those as you go forward and continue to review. I do want to talk a little bit about a pattern here with respect to gases. And earlier we had talked about the pressure, and we saw that as the pressure increases, the solubility increases. There were a couple of laws here that we were looking at in the class, and so just a little bit of a review here. Let's bring those to the forefront. So let me make a little bit of room here, move this up to the top. There were a couple of rules here, and so let's kind of do this here. I will put this here and then bring these down. There were two rules. One of them was Henry's law, and then the other one was Raoult's law. Now, the main thing here to know is that both of these are related to pressure. In the case of Henry, the equation that we're interested in here is going to be the equation with where the concentration is going to be equal to the constant of for Henry's constant multiplied by the pressure. Now, just be familiar with what this is, but essentially what's going on here with this particular equation is when you look at the relationship here in terms of the concentration, what we saw here was that the mass is what was related to the pressure. So it was a relationship there, and a lot of it had to do with that concentration of the gas in solution. So in other words, how much was actually dissolved, that was proportional to the pressure of the gas in terms of what it was experiencing. So the equation is very helpful for us. Just remember that. So here, the mass of the gas is proportional to the pressure of the gas. And so that's true there for Henry's. Now, for us, the one that will probably be a little bit more applicable for us to remember and to keep in mind is going to be Raoult's law. And Raoult's law talked about the pressure from a slightly different perspective, and that was looking at the pressure of the solution is going to be equal to the mole fraction of the solvent. And this is going to be multiplied against the pressure of the solvent. And so typically what we will do here is we would be asked to figure out what's the pressure of the solution, because if you understand the pressure of the solution, then that would tell you whether you're going to get the solubility of that particular gas. So one way of kind of interpreting all of this was in a pure solvent scenario, then the only thing that's actually being considered is the pressure of the solvent. But the second that you introduce a solute into the mix, this solute is going to actually reduce the solubility, because of the pressure that's actually going to be experienced by the solution is actually going to be affected in a negative way. Largely because the mole fraction that's associated with the solvent is going to be impacted here. So this is what I mean. So in class we had gone over this, and so let me just briefly go through this one more time as quickly as I can, and then just go ahead and make sense of that as you kind of try to solve some of these problems for Raoult's. So let's go ahead and make some space here. Let's get Henry's law and other items out of the way. And so we'll put that there, and let's get a divider. And so let's split this out. And so this is what I had shared before in an example. So essentially here, we know that the pressure of the solution is going to be equal to the mole fraction of the solvent multiplied by the solute. So essentially, we don't have any solvent. Essentially, what's going to happen here is that the pressure of the solution is going to wind up equal to the pressure of the solvent. And so if we're using pure water, whatever pressure is given to us here, that'll be the same thing there. So you should be able to have equal pressures, and since the pressure is the same, there's no lowering of the pressure, then if we have a scenario where we have a beaker, say we have a solution in here, all these particles of solution in here then have an easy way or a readily accessible way of actually exiting the solution from the liquid phase and going into the gas phase. And so we should be able to have a certain amount of gas particles up here. So that means that the gas particles or the water molecules or the solvent molecules here are able to go from the liquid phase into the gas phase. And so what you would tend to find is that in this section up here, we would actually have a high degree of pressure or vapor pressure. And so here what we'll find here as the vapor pressure goes up, what that means is that the solubility actually goes up as well. And in contrast, what if we were to add some solvent? So let's represent the solvent. Let's say that we put the solvent here, or the solute. We add a solute into the mix. When you add a solute to the mix, what's going to happen is you're going to get some particles here. And some of these particles might end up being here at the surface. And so let me zoom in on that for a little bit. So what tends to happen is when you've got these, some of these particles get in the way. So some of the water or the solvent particles can't go up. And so what's going to happen with that solute is that the amount of vapor pressure actually is going to reduce. So you're going to wind up getting a reduction here of the vapor pressure. So here, if we do this here with the solute, what we wind up seeing is that the vapor pressure goes down. And if that happens, the solubility goes down as well. And so that's something to consider here. Now you can figure that out if you actually do the math here. In terms of the mole fraction, that means that the value here for the mole fraction is going to increase. The second that you start adding solute to that mix, you'll wind up getting a reduction in the pressure. And so that's going to be a bad thing overall in terms of solubility. All right, so one of the last things that we needed to talk in this section is going to be the discussion on dilutions. And so let's go ahead and address those here. So a dilution is essentially going to follow the equation here of M1V1 equals M2V2. And for the most part, these types of problems are going to give you 3 of the 4 variables here. You'll have to consider what happens with volume. Sometimes the examples give you start off with a certain volume, then there's a change in volume, either up or down. As long as you keep track whether you're adding more solvent volume or you're reducing it by evaporation, if you just keep that in mind, you should always be able to figure this out. And ultimately, though, you might be asked to figure out either an initial concentration or an initial volume, and that doesn't really matter in the grand scheme of things because you should be able to figure that out quite easily overall. So just be prepared to do that, but you should also know what a dilution is, just out of definition. From a definition aspect, know that a dilution goes from a high concentration. You're going to wind up going to a lower concentration is the definition of a dilution. So typically you'll begin with a container, say you start off with a concentration of 3 molar, for example, and you go down to a lower concentration, let's say 1 molar. If you started, for example, with, let's say 300 milliliters here, the question would be, what is the volume here that we're going to need overall to get to this desired concentration? So in this particular example, if I were doing this here, let's create a little bit of room. If I were doing this problem here, what I would do is I would say, okay, so we're trying to figure out the second volume, so that would be V2. So if I start off with that equation, M1V1 is equal to M2V2, I'm going to go ahead in here and I'm going to look for the second variable. So let's do a little bit of algebra, manipulate it, you wind up getting the following. V2, my second volume, is going to wind up being M1V1 divided by M2. So all you would need to do now is plug in the information here. For M1, I would put 3 mLs. And so let's go ahead and do that here quickly. So that would be 3 molar. We're going to multiply that by the first, so that would be 0.3 liters. And then we're going to divide that by the second concentration, which is 1 molar. And this should give us the value here for the second volume. If we do the math here, you're going to wind up getting the following. So the volume here should be 0.9 liters is what you need there as a, so this is going to be liters needed. Okay, and so as long as you can figure that out, you should be okay in this section here. So Go ahead and continue your preparations. In the next video, we'll finish this off in the last section, 3.13, looking at the Beer-Lambert equation. See you then.